Python lecture. So today we have two main topics. First, I want to finish off the topic from last week. That was how to become a better Python programmer. And there's two more things that you really need to learn about. The first one is modules, and the second one is packages. So we'll spend the first probably half an hour with this, and then we'll move on to numerical computations with Python. So that's going to be a very important part for the rest of the class, actually. Okay, so modules and packages are essentially another two ways on how you can structure your code in a better way. And they become important when your program becomes larger over time. So, when you only have a few statements, then you reuse these statements, then you started packing these statements into a function. And then we said, well, if you have multiple functions that belong together in variables, then we pack them in a class. And now this hierarchy just continues. So if you have multiple classes and multiple functions that you believe should be kind of together, maybe some kind of library, then you would pack this into a module. And then if you have multiple modules that you would like to share online, for instance, then you pack them into a package. Okay, so that's the overall idea. So we start with modules, and then I talk about packages afterwards. Yeah? Yes, you can tell. Thanks for pointing this out. For some reason, I completely ignore this when I talk. So I only hear it when someone reminds me. Okay, so Python modules. A Python module is simply a file with Python code in it. So there's nothing special, so to speak, about a Python module. And so in this module file, you can have functions, you can have variables, you can have classes, and you might even have runnable code inside that module. And so why would you want to use modules? Well, they allow you to structure your code. You don't have to write your entire code in just a single file, but they allow you to split the code into multiple files. So this can be used for easier maintenance, for instance, to make logical parts of the code. You can separate it into each file. Also, what modules are really useful for is if you have common functionality that you want to reuse between different projects. Right? Then you just create one module that contains these features, and you can share that module across your different projects. And finally, of course, once you have a useful module that you use for multiple projects, but maybe also other people would like to use it, then you can publish this module on the web for other people to use. But I will actually show you an even better way, and this is the layer above, namely packages. So normally what you share online are packages rather than modules. So we've used modules already, or we're going to use them in our assignment. So Python comes with this bunch of standard modules that is available in every Python environment. And so you've for sure already used a module called sys. And the way you use this is that you first use an import statement to import the functionality in this module. So import sys loads this module. And then we can use all the variables and functions that are defined in that module. So for instance, the sys module has a variable called argv, and that variable is a list. So you can write sys.argv and get the second command line argument, for instance. So instead of loading the entire module with import sys, we can also import only one variable or class or function of that module. So if you write from sys import argv, then in the code below, we only have access to this argv variable, but we can't access the sys or any other functionality that sys provides. And so it's generally fairly good. It's fairly good practice to say that if you only use a few selected parts of a module, then it's better to use this syntax, where you import only the parts that you actually need of that module. But if you have a module where you make extensive use with many, many functionalities, then you might want to use this syntax up here. There's another way of importing functionality from modules, and that's to write from sys import star. So here the star is essentially a placeholder and just means, okay, load everything that is in the sys module. But that's not recommended to do that. And the reason is because you might load variables in here that you're not even aware of and overwrite them later on in your script. So for instance, here this next line, this will work just fine because argv is a variable in the sys module, so we can access it just fine. But then maybe later on in your program, you decide that you want to use a variable, use flex equals, and you set it to an empty string. But now the problem is that it turns out that the sys module also has a flex variable, right? And so now without knowing, you start kind of interfering between module variables and your own local variables. And so this can be dangerous. So in general, this kind of implicitly loading everything that is contained in a module should be avoided if there are not very good reasons for it, or if you have very good control on what this module contains. So the beautiful thing with modules is that they're really, really simple to create. So the kind of the threshold from going from a simple script to modularizing your script is extremely simple. And so the way you create a Python module is just consists of a single step. You create a Python file, and you put in any code that you want to have in that module, and that's it. Okay? So and that can be variable, functions, or classes, essentially. So our very first module that we're going to implement is this one here. So it's inify mymodule.py. So I use the same .py extensions, just like other scripts. And then you can see here I define a variable and I define a function. And so of course now if I was just executing the script, if I could just write Python mymodule.py, but then nothing would happen, right? All I do is I define a variable and I define a function, but I never execute that function. So executing modules doesn't really make that much sense to begin with. They're really only useful if you start importing them. So then how do we use this module that we just created? Well, assuming that we are in the directory where the Python file lies in, then we can just write import my module, right? So now we use the same file name, but we don't use the .py extension. And so now I have access to all the variables that are in that module. So for instance, I can write mymodule.greet. Of course, I could have also written from my module import greet and then just use the greet function immediately. Okay, so here's a syntax that I haven't shown you yet, but this is also useful in many cases. So sometimes it becomes a bit annoying to always write out my module, and just because we are lazy programmers, so then we just define an alias, a short notation of that. And then instead of always having to write my module, and now I can just write mm.greet. Yeah?
For the importing process, is it important that my module is in the same working directory as my Python code?
Yeah, so it is. I will show you.
How can I do it if it's in a different directory? Just provide the path in the import statement? Or?
You will learn about this. So the question is, what do my modules need to be in the same directory as my scripts? And for now, we assume that that's the case. But if you wait 15 more minutes, then you learn how this can be generalized. Yeah, and so of course, this was the last use case, right? So here, if I want to make use of that function immediately, I can write from my module import greet and then just call the function. And just to demonstrate this, so of course, remember this my module also defined the variable name. So of course, I can also access the name directly, right? I can also write from my module import name and then print name. So as I said before, executing modules doesn't really make a sense very often because they don't usually you don't put runnable code in your module. You only put definitions of variables and functions in there. But sometimes, and so I think that's actually fairly good practice. What I do is when I develop a complicated, so the idea, right, when you create modules is that they collect all types of code that have similar functionality. So for instance, if I make I have some geometric computations, and then I create a module that contains computations with points, for instance, and maybe a point class and a circle class, and all this could be kind of in one nice module called geometry.py, right? And that contains all the functionality that operates on these types of geometries. And so often when I am, of course, and then you should add doc strings and so on. But sometimes it's actually useful to have just some test code at the very end of the module for my reference to see how this module can be used. Just some simple test cases. And there's a trick on how you can do that. So if you have this if statement down here, if __ name equals _ main, then and you add some code in here, then this code will only be executed if you use that module as a script, right? So if you write Python mymodule.py, then it will run all the code that was up here, and it would also, this if statement becomes true, and then it would run the greet function. So this, but if you do import my module or from my module import greet, then this code will not be executed. So in a way, this gives you the, the way I use that is I almost always have this if statement at the end of my module, and then down here, I have some sample code where I can just test the basic functionality of that module. And then, yeah, I almost use it almost like a simple test feature. I just run the module, assuming that it was a script, and just make sure that everything runs quickly. So this is just a little tip, a good practice tip that I often make use of. Yeah, so that's it with modules. So now we come to packages, which is one layer above the modules. And packages is essentially, think of packages of directory, is a directory that contains Python modules. So now we're talking about larger projects where you might think, maybe my geometry module became so lengthy that now I want to break it up. I want to have I want to have multiple modules, maybe one module that operates points, another module that operates in circles, and so on. So you end up with kind of 5 modules. And these modules are you now put in a directory, and that directory is called a package. It collects multiple modules. So a package is a hierarchy file directory structure that consists of modules. But of course, you can, in a package, contains modules, but you can also, again, contain a directory which contains modules, right? So these things can be nested. So you can have a package, and then in that package you have modules and another package, and so on and so forth. And so once you created this, the usage is very similar from a developer's perspective. So instead of just writing from SciPy, if SciPy was a module, you would just write from SciPy import minimize. But it turns out SciPy is a package and optimize is a module. So then you have to write from SciPy dot optimize import minimize. Okay? And it's these packages that are typically distributed on the web and also installed system-wide, for instance. Yes, so as I mentioned before, so there's some packages that are installed by default in a Python environment, but there's many other packages that you can can be downloaded. And that's part of the reason why Python is actually, well, that makes Python so powerful, because there's so many packages out there that for many of the problems that you might encounter in kind of a real-world programming, so to speak, there's probably a package that helps you doing that already. So just the most kind of fundamental packages that you will find in Python that are not installed by default, so you will have to install them, is SciPy, it's scientific Python libraries, Numpy, or Numpy, numerical Python, that's going to be the topic of the next lecture. IPython, it's an interactive Python, and we will actually have a guest lecture on IPython maybe next week or in 2 weeks. Matplotlib allows you to do plots, and Pandas is a data analysis platform that we also cover in a future lecture. And so all these packages can be installed. And so how do you install these? Or how do you know about the packages that are available for Python? Well, you can use Conda if you work with Anaconda, but you can also use pip, which is kind of the Python package manager. So you can search for packages with the command pip search and then a keyword. So if you did pip search, probably numerical Python, you should get Numpy as an answer, as a possible answer. And then if you've identified which package you want to install, then you can type in pip install and then the package name. And then you have 2 options. So either you want to install it system-wide, and if you want to install it system-wide, then you leave out that user here. So you just do pip install package name. But then you need to have root access to your system. Otherwise, you get an error message saying no permission to install the files in the system folders. But if you anyway only working with if you only need that package for the user that you logged in, then you can add this option --user, and then it will install it in your local home directory. And for that, if you add that option, then you don't need root access. So specifically on the EFI machines, you will always have to use, you should use this if you're not in an Anaconda environment. So how do you create now? So I just explained you how you use packages. Now I'll show you how you can create your own packages. A package is, in simple words, a package is simply a directory in which you put, so the simplest package that you can create is a directory in which you have an empty file that is called __init__.py. As soon as you have that, we are talking about a Python package. And then in addition, you can put in module files inside that package to make it a more interesting package. So and that's essentially it. So here's a example file structure of a package. So this is a solver that I've implemented some time ago. It's a solver for partial differential equations. And I mean, these solvers, they need various different functionalities. So I decided to split it up into a package and modules. And so you can see I have one base package called PDE solver. And then in order to make it a package, I need to create an empty init file in here. But then again, I decided to kind of split it up into multiple sub-packages. So I have one sub-package called numerics. And again, I create an init file to make it a package. And then in that numerics, I have another sub-package called PDE, again, making it a package using the init file. And then finally in here, I have my module where the actual interesting code is in. Right? And so let's just assume for a second that in this grids.py, we have a function or FDM grids that we can import now. So I just want to show you how this works. So now if you wanted to, let's say you have this structure here and you want to use this object here, then, okay, what you need to do is you need to do from, and now essentially you have to follow down the directory structure. So it's PDE solver is the main directory, then the subpackage numerics, so PDE solver.numerics, then another subpackage .pde, then the module file .grids, and then import, and this is the object that we're interested in. So yeah, this should be capitalized. So import FDM grid. Okay, and then I can use this. This is a class, and so I can initialize it and run it. But essentially, when you use these packages, you essentially just follow down the directory structure that you defined in your package. Okay. So now comes the question: how does Python find these? If you write import sys or import my module, how does Python find these packages? And there's 3 steps that Python performs. So there's multiple places where it's looking for. And the most important ones are 3 that I've listed here in the following order. First, it checks if that package or module is in your current directory where you run the Python script. And if that's the case, it just uses that. Then it checks the paths that are defined in an environment variable called Python path. So Python path is a bunch of directories that you can specify. And it goes through all of these and checks if it can find the module on the package or the package in there. And then if it still can't find it, then it checks some global paths. So Python has some standard installation paths where packages are installed to, and it will go through these and check if your package is installed. If it still can't find it, then you get an error message. So now, right, I mean, we have multiple options. The first one is, of course, to leave our package in the directory in which we are working on. So that's kind of a local solution. That isn't ideal if you have multiple projects that you want to have that want to use that package, because then you would either have to copy around that package to the projects, or you would have to do your development in one directory only, which is not ideal. So instead, what we could do is we could have our package or module in one directory and then make it available wherever we are in our bash environment. So this option 2 was to add the module path to Python path, and this is how you do it. So assume that I've developed my module in this directory home, Simon, mymod, and then I can make I can ask Python to check that path with the following command here. So essentially what this does is I define the environment variable Python path, and I set it to home Simon MyMod, : and then I append the original value of the Python path. So I just add another directory to the Python path. So this works fine. You just need to be aware that this, if you type this into your bash shell, this is just a local change to your current bash terminal. So as soon as you close that bash terminal, and you open it up again, then you would have to retype these commands here. So a better solution is to make your package installable. So the idea is that once it's installable, then you can use pip, so this package installer, for your own package, just like use the pip installer for any other package, right? So then suddenly your package becomes an installable package that you could also share with other people. So the way you make your package installable is to add another file to your package, and you need to add it to the root folder of your package. And that file needs to be called setup.py, and it has this format here. This you can essentially just, it has always the same structure. We use this package called distutils and import the function setup. And setup takes 3 main arguments that you need to provide. First, you need to specify a name of your package, and then a version name, and then a list called packages. And this is all the root folders of the packages that you want to have installed when you run pip. So in the PDE solver case, it was just the folder PDE solver that contained, I only had one package. So I asked this setup routine here to install that package for me. And so now if you've done that, you can just use a pip or pip, it depends on your system, either pip or pip3, install, and then you use a dot here to just specify that you want to install the package that is in my current directory. So assuming that the setup.py is in the current directory, then you can run this. And then you can again use the -- user if you want to have it user-wide or system-wide, then you leave it out, but then you need root. So I can just, maybe I can demo this to you. Let's see if we have, so I'm in the, so I'm in a folder called PDE solver. Where can you see? Here, PDE solver. And you can see this folder has setup.py. Okay, this is the content that I just showed you. And then we also have a directory PDE solver. And then if we go in here, you can see I have the init file, and I have the numerics folder. In the numerics, there's again an init file, and so on and so forth. Okay? But so now if I'm in this directory here, and I open an IPython shell, I can write import PDE solver. And then I can, for instance, check solver. Okay, this is a module. And here's a trick. So sometimes you're not entirely sure. Maybe you're not sure if you're importing a local module or package, or maybe a system-wide installed package. And there is this hidden variable called __file__ that you can always, that always exists for packages and modules, and that returns. So you can print this out. It's a string that contains the path to that module. And so here you can see, I mean, this is a long path, but essentially you can see that this is now my local module that I've imported. So not a kind of a system-wide installation of maybe a module of the same name, but it's really the local one. Okay, but now, because I have this setup script, I can write pip3 install dot -- user. Takes a second. Okay, and now it has installed it. So now I can go outside that package directory, and I can see if I can still import the package. So if I do pd solver, okay, so this still works. And now we can check where this has been installed to. Okay, and you can see now I'm loading this module from this is the path where pip decided to install my package. Right? So I don't really care where it is, but it's now available wherever I am. And if I decide that I don't want it anymore, then I can write pip uninstall pd solver. Okay, so it asks me if I'm sure. I'm sure. And then if I load IPython up again and try to import it, then I get an error message saying it's not available. So just to summarize, this is how any larger Python project should look like, or is a good guideline on how it might look like. So you have your main directory. Also, this is recommended for your assignments. For instance, for assignment starting from assignment 4, this is kind of quite a good guideline for your structure. So you have your main folder. This might be assignment 4, for instance, or in my case, it's the PDE solver. Then we have a setup.py file that installs the packages and modules that we're developing. Then one file that I highly recommend is to always have a README file that specifies what your package, just a quick introduction on what this package does, how you can install it, and maybe a rough user guideline on how to run scripts that you've implemented. Then we have the package itself. The package itself, so this is the directory structure with the init files and then your module files in here. And then you might also have some tests down here, right? So I normally collect all the tests, the py.test tests, in a directory called tests. Okay? Does that make sense? Any questions? No? Okay, then let's continue with the second part. So now we talk about numerical Python. And so the package that we're talking about is called Numpy, or Numpy. And Numpy is kind of the basis for many, many packages. It's kind of became essentially the standard for any heavy computations that you do in Python. So whenever you work, you might, in future, maybe even if you don't work with Numpy directly, any packages that do heavy computations rely on Numpy at one point or the other. So it's really, really useful to understand how it works and why it works so well. And so, I mean, of course, the first question that you might ask is, why do we need a specific module for numerical computations? Why can't we keep doing what, I mean, we already know how to add numbers and perform computations in Python. Why not just continue? And to understand what the problem is, we need to understand how Python works. So when you run a Python script, what it does is it reads that .py file and it compiles it into a so-called byte code version, which is essentially the original script, just a little bit more machine friendly. And then Python interprets this code By the way, these bytecodes, they're called .pyc files. So you sometimes see them. Once you run your script, you suddenly have some .pyc files. And these are your bytecodes. And if you can delete them if you want, and you certainly also you should never check them into your GitHub account, GitHub repository. If you delete them and you run your script again, Python will just regenerate them. Yeah, and so Python then interprets this bytecode, which means essentially that it executes the code line by line. Okay, and so this is some consequences in terms of performance. So text processing, if you do any terms of text processing, doing this interpretation of the bytecode doesn't really affect your performance so much, and often you get similar performance as you would get if you did a pure C implementation. However, if you have for loops where you loop over large amounts of data, right? Maybe this here you're looping over a list, and that list might have 1 million entries. Right? Maybe you're performing some operations on images or even videos, and you have a list like this, then this byte interpretation becomes very, very slow. And yeah. And so in contrast, if you have a compiled language like Fortran, C, and C++, they don't do an interpretation of every line, but instead they have this compiler step. So they compile the source code into assembly code, and during this compilation step, they can do really, really good optimizations, especially in loops like this. And then they outperform Python by orders of magnitudes. I'll show you examples. So often C++ can be hundreds of times faster than Python in these cases. Okay? So that's a problem, right? So Python really sucks in kind of these loops. So how do we solve that? Well, the way we solve that is that we take the slow parts of our Python code and implement it in C and C++, right? So we take most of the code, most of the runtime. If you look at a typical program, a Python program, most of the runtime is spent in tiny pieces of the code, and that's typically in these kind of loops. And exactly these types of loops that we now move from a Python code to a C implementation. And so, and the way we do that today is with Numpy. I'll show you another ways how you can do that in a future lecture. But just to give you some runtime examples here. So very simple example. So I read in 100,000 X and Y data points from a data file, and then I write it out again, the X point, and then the Y point applied to a Python function, or to a function F here. And here you can see the different runtimes for different implementations. So you can see pure Python takes around 4 seconds. So 100,000 is not so large, so you would see much bigger effects if you used larger lists. But pure Python takes around 4 seconds. Then we have Perl, which is another interpreted language. It takes 3 seconds. Tcl is another older interpreted language that's really slow, as you can see, 11 seconds. And then we have C. So C takes 1 second because of that optimization of the compiler. Then we have C++. So you can see that actually C++ has quite some overhead over C. So it's 2.5 or 3.5 times slower. But now we get Python using the Numpy package that we're talking about now. And now we can reduce from the 4 seconds, we can go down to 2.2 seconds. So suddenly, our Numpy implementation with a slow Python interpreter is competitive to at least C, but certainly with C++. So how can it be so fast? So Numpy, well, first of all, the Numpy module is written in C in Fortran itself. So all the slow code have been re-implemented in C, and you're actually executing C code when you perform these operations in Numpy. And also Numpy is very clever when it comes to aligning data in memory. So as you might know, the CPU actually getting data from memory can be very, very slow in contrast to how fast the CPU works. So it's very important to always get as much relevant information to the CPU as possible. And the way you do that is to cluster together all the especially arrays that you're working with should be as close as possible in your memory. So it shouldn't be sprinkled around over the entire memory that you have. So I mean, Numpy isn't the first package that provided numerical Python. There was numeric in the mid-90s and numarray from 2000. Numpy was created in 2006, and today it's essentially the quasi-standard. So I won't even talk about the other packages anymore. Okay, so just some links here if you're interested in diving more into details, but I hope I give you a good overview today. So before we have the break, I just want to give you a small, well, not so small example of Numpy, and after the break we go through that code line by line, but I just want to show you what it does. So the task of this demo is to fit a line through some X and Y data points. So maybe let's just look at the result. So I mean, you can see that it probably takes around 25 lines of code, or maybe 30, that we will dissect in a second. But the task of this exercise is that we have some, actually maybe you should call it machine learning to make it, I mean, this is the new word. So we're doing machine learning here. We have some data points, right? This is our training data, right? So some X and Y points. These are the blue dots that we've observed. And the task is to fit a line through this data that is kind of optimal in a way that matches the data as best as possible, right? And yeah, I need to talk about what best means in that sense. But okay, so this is the blue line is the one that we computed from the blue dots here. And of course, you can ask, how did I generate the data, these blue dots? Well, I took a true line, so the ground truth, I call it, which is the red line, and then I added some noise to it. So essentially, these blue dots are just, I evaluated this red line here, and then I added a little bit of noise. Okay, and so we can run this code multiple times. So, and then every time you will get a slightly different answer. Right? So this was a really good fit. Here it wasn't quite good, so you can see quite large errors here. Yeah. Okay, so after the break, we'll go into that script and I'll explain to you how it works. Let's start again at 1:15. Of course. Just 1 second. I need to make sure that I